In this chapter, we zoom into the organizational aspects of data management. It is based upon our book, Principles of Database Management, published by Cambridge University Press. You can find more information about our book on the website at the bottom of my slide. My name is Bart Baasens, and I'm one of the authors of the book. The first part of the chapter zooms in on data management. The second part reviews various roles in data management, such as information architect, database designer, data owner, data steward, database administrator, and data scientist. Data management entails the proper management of data and the corresponding data definitions or metadata. It aims at ensuring that data and metadata is of good quality and thus a key resource for effective and efficient managerial decision-making. In what follows, we first review catalogs, the role of metadata, and the modeling thereof. This is followed by a discussion on data quality and data governance. The importance of good metadata cannot be understated. In the past, this was often neglected, resulting in significant problems when applications needed to be updated or maintained. In the file-based approach to data management, the metadata was stored in each application separately, creating various issues, as discussed earlier. Just as raw data, also metadata is data that needs to be properly modeled, stored, and managed. Hence, the concepts of data modeling should also be applied to metadata in a transparent way. In a DBMS approach, metadata is stored in a catalog, sometimes also called data dictionary or data repository, which constitutes the heart of the database system. This facilitates the efficient answering of questions such as which data is stored where in the database, who is the owner of the data, who has access to the data, how is the data defined and structured, which transactions work with what data, are the data replicated, and how can consistency be guaranteed? Which integrity rules are defined? How frequently are backups made? The catalog can be an integral part of a DBMS or a standalone component which must be updated manually. Obviously, the integrated solution is to be preferred and more prevalent in modern-day DBMSs. The catalog provides an important source of information for end users, application developers, and the DBMS itself. Remember, the data definitions are generated by the DDL compiler. The DML compiler and query processor use the metadata to solve queries and determine the optimal access path. The catalog should provide support for various functionalities. It should implement an extensible metamodel for the description of the metadata. It should have facilities to import and export the data definitions and provide support for maintenance and reuse of metadata. The integrity rules stored should be continuously monitored and enforced whenever the raw data is updated. By doing so, the catalog guarantees that the database is always in a consistent and correct state. It should support facilities for user access by clearly defining which user has access to which metadata. The catalog also stores statistics about the data and its usage. These are extensively used by the DBA for performance monitoring and tuning. Also, the query optimizer of the DBMS relies on these statistics to determine the optimal execution path of a query. A metamodel is a data model for metadata. A metamodel determines the type of metadata that can be stored. Just as with raw data, a database design process can be used to design a database storing metadata. As already discussed, the first step is to design a conceptual model of the metadata. This can be either an EER model or a UML model. This figure shows an example of a metamodel, which is in this case an EER conceptual model of an EER model. The relationship types R1 and R2 model the relationship between an attribute and an entity or relationship. The relationship type R3 specifies which entities participate in which relationships. The relationship type R4 connects a relationship to its roles. R5 and R6 model the entities that participate in a generalization, either as a superclass or a subclass. Note, we assume that every generalization has one superclass, see relationship type R5, and one or more subclasses, see relationship type R6. Data quality is often defined as fitness for use, which implies the relative nature of the concept. Data of acceptable quality in one decision context may be perceived to be of poor quality in another decision context, even by the same business user. For instance, the extent to which data is required to be complete for accounting tasks may not be required for analytical sales prediction tasks. Data quality determines the intrinsic value of the data to the business. Information technology only serves as a magnifier for this intrinsic value. Hence, high-quality data combined with effective technology is a great asset, but poor quality data combined with effective technology is an equally great liability. This is sometimes also called the GIGO, or garbage in, garbage out principle, stating that bad data results into bad decisions, even with the best technology available. Decisions made based on useless data have cost companies billions of dollars. A popular example of this is the address of a customer. It is estimated that approximately 10% of customers change their address yearly. Obsolete customer addresses can have substantial consequences for mail order companies, package delivery providers, or government services. Poor data quality impacts organizations in many ways. At the operational level, it affects customer satisfaction, increases operational expenses, and will lead to lowered employee job satisfaction. Similarly, at the strategic level, it affects the quality of the decision-making process. The magnitude of data quality problems is continuously being exacerbated by the exponential increase in the size of databases. This qualifies data quality management as one of the most important business challenges in today's database economy. Data quality is a multidimensional concept in which each dimension represents a single aspect or construct comprising both objective and subjective perspectives. Some aspects are absolute, whereas others depend on the task and/or experience of the data user. Therefore, it is useful to define data quality in terms of its dimensions. A data quality framework categorizes the different dimensions of data quality. Different data quality frameworks exist, but the prevalent one is the framework by Wang et al., which has 4 categories: intrinsic, contextual, representation, and access. The motivation behind the framework was to capture a broad conceptualization of data quality as perceived by data consumers instead of IS professionals, since they are the ones using the data. The framework provides a means to measure, analyze, and improve data quality in a valid way. It was built using a 2-stage survey combined with well-established empirical research methods. The intrinsic category represents the extent to which data values are in conformance with the actual or true values. It denotes that data should have good quality. Example dimensions are accuracy, objectivity, and reputation, as you can see defined here. The contextual category measures the extent to which data is appropriate to the task of the consumer. Obviously, this can vary in time and across data consumers. You can see the dimensions completeness, appropriate amount, value added, relevance, timeliness, and actionable together with their definitions. The representation category indicates the extent to which data is presented in a consistent and interpretable way. Hence, it relates to the format and meaning of data. Example dimensions are interpretable, easily understandable, consistency, concisely represented, and alignment, as you can see defined here. The access category represents the extent to which data is available and obtainable in a secure manner. This is especially important in today's networked environment, with data being distributed across various platforms. Example dimensions are accessibility, security, and traceability, as you can see defined here. Obviously, high-quality data should be intrinsically good, contextually appropriate for the task, clearly represented, and accessible to the data consumer. Some dimensions lend themselves to objective assessment that is intrinsic to the data itself, independently from the context in which the data is used. Other dimensions cannot be measured in absolute terms and vary with the usage context or task at hand. Let's now discuss some of the most important data quality dimensions. Accuracy refers to whether the data values stored for an object are the correct values. The accuracy dimension is heavily correlated with other data quality dimensions. Often, a quality issue initially labeled as an accuracy problem will turn out, for example, to be a matter of representation. For example, US versus European decimal notation. Or timeliness. For example, customer address is obsolete after root cause analysis. The completeness dimension can be viewed from at least three perspectives: scheme completeness, column completeness, and population completeness. By scheme completeness, we refer to the degree to which entity types and attribute types are missing from the scheme. An example of a scheme completeness problem could be a missing order entity type or a missing email address attribute type. Column completeness considers the degree to which there exist missing values in a column of a data table. An example of a column completeness problem could be a missing value for a customer's birth date. Population completeness indicates the degree to which the necessary members of a population are present or not. An example of a population completeness problem could be that important supplier entities are missing for the supplier entity type. The consistency dimension can also be viewed from several perspectives. For example, one can be concerned about the consistency of redundant or duplicated data in one table or in multiple tables. Different data elements representing the same real-world concept should obviously be consistent with one another. Another perspective would be the consistency between two related data elements. For example, the name of the city and the postal code should be consistent. Consistency can also refer to consistency of format for the same data element used in different tables. Otherwise, two values can be both correct and unambiguous, but still cause problems. For example, the values New York and NY may both refer to the same city. The prior examples of inconsistencies will typically be symptomatic for underlying problems with other data quality dimensions, such as accuracy or completeness. The accessibility dimension reflects the ease of retrieving the data from the underlying data sources. Often, there will be a trade-off between the security and accessibility dimensions. The more measures are in place to enhance security, the more obstacles may be introduced to obtain access to the data. Such trade-offs are common between data quality dimensions. Another example is the possible trade-off between timeliness and completeness. The higher the pressure to deliver the data promptly, the fewer measures can be taken to detect and resolve missing values. Data quality is a multidimensional concept. Hence, data quality problems can arise in various ways. Common causes of bad data quality are multiple data sources. Multiple sources with the same data may produce duplicates, a problem of consistency. Subjective judgment in data production. Data production using human judgment, for example opinions, can cause the production of biased information, a problem of objectivity. Limited computing resources. Lack of sufficient computing resources and/or digitalization may limit the accessibility of relevant data, a problem of accessibility. Volume of data. Large volumes of stored data make it difficult to access needed information in a reasonable time, a problem of accessibility. Changing data needs. Data requirements change on an ongoing basis due to new company strategies or the introduction of new technologies, a problem of relevance. Different processes using and updating the same data, a problem of consistency. These causes of data quality problems have always existed to a certain extent since the beginning of the digital era. However, initially most data processing applications and database systems existed in relative isolation. As so-called silos. This was far from an ideal situation from a company-wide data sharing perspective, but at least the producers and consumers of the data were largely the same people or belonged to the same department or business unit. One was mostly aware of which data quality issues existed with one's own data and people would often deal with them in an ad hoc manner based on familiarity with the data. However, with the advent of business process integration, company-wide data sharing, and using data from various operational systems for strategic decision-making, the data producers and consumers have been largely decoupled. Therefore, people responsible for entering the data are not fully aware of the data quality requirements of the people using the data, or of the different business processes in which the data is used. Moreover, different tasks using the same data may have very distinct data quality requirements. To manage and safeguard data quality, a data governance culture should be put in place, assigning clear roles and responsibilities. The aim of data governance is to set up a company-wide, controlled and supported approach towards data quality accompanied by data quality management processes. The core idea is to manage data as an asset rather than a liability and adopt a proactive attitude towards data quality. To succeed, it should be a key element of a company's corporate governance and supported by senior management. Worldwide international regulatory institutions have further amplified the importance of data governance through business-specific compliance guidelines. For example, the Basel and Solvency Accords provide clear guidance for data governance within a credit risk and insurance context. Different frameworks have been introduced for data quality management and data quality improvement. Some are rooted in general quality management, while others focus explicitly on data quality. Another category of frameworks focuses on the maturity of data quality management processes. They aim at assessing the maturity level of data quality management to understand best practices in mature organizations and identify areas for improvement. Popular examples of such frameworks include Total Data Quality Management, TDQM, Total Quality Management, TQM, Capability Maturity Model Integration, CMMI, ISO 9000, Control Objectives for Information and Related Technology, COBIT, Data Management Body of Knowledge, DMBOK, Information Technology Infrastructure, Library, ITIL, and Six Sigma. Most frameworks are scientifically grounded and consider the perspective and knowledge of various data stakeholders across different industries. The TDQM framework is illustrated here. A TDQM cycle consists of 4 steps: define, measure, analyze, and improve, which are performed iteratively. The define step identifies the pertinent data quality dimensions as discussed before. These can then be quantified using metrics in the measure step. Some example metrics are the percentage of customer records with incorrect address, accuracy, the percentage of customer records with missing birth date, completeness, or an indicator specifying when customer data was last updated, timeliness. The analyze step tries to identify the root cause for the diagnosed data quality problems. These can then be remedied in the improve step. Example actions could be automatic and periodic verification of customer addresses, the addition of a constraint that makes birth date a mandatory data field, and the generation of alerts when customer data has not been updated during the previous 6 months. If actual data quality improvement is not an option in the short term, for reasons of technical constraints or strategic priorities, it is sometimes a partial solution to annotate the data with explicit information about its quality. Such data quality metadata can be stored in a catalog, possibly with other metadata. In this way, the data quality issues are not resolved, but at least data consumers across the organization are aware of them and can take the necessary precautions as part of their task execution. For example, credit risk models could incorporate an additional risk factor to account for uncertainty in the data derived from data quality metadata. Unfortunately, many companies still ignore data quality problems because of a lack of perceived added value. Hence, many data governance efforts, if any, are mostly reactive and ad hoc, only addressing the data quality issues as they occur. In what follows, we discuss various types of job profiles within the context of data management. We introduce the information architect, database designer, data owner, data steward, database administrator, and data scientist. Each of these roles are essential in ensuring high data quality and transforming data into actual business value. Depending upon the size of the database and the company, multiple profiles may be merged into one description. The information architect, also called information analyst, designs the conceptual data model, preferably in dialogue with the business users. He or she bridges the gap between the business processes and the IT environment and closely collaborates with the database designer, who may assist in choosing the type of conceptual data model, for example ER or UML, and the database modeling tool. The database designer translates the conceptual data model into a logical and internal data model. He or she also assists the application developers in defining the views of the external data model. To facilitate future maintenance of the database applications, the database designer should define company-wide uniform naming conventions when creating the various data models. Every data field in every database in the organization should be owned by a data owner, who is in the authority to ultimately decide on the access to and usage of the data. The data owner could be the original producer of the data, one of its consumers, or a third party. The data owner should be able to fill in or update its value, which implies that the data owner has knowledge of the meaning of the field and has access to the current correct value, for example, by contacting a customer, by looking into a file, etc. Data owners can be requested by data stewards, which we discuss in a second, to check or complete the value of a field, as such, correcting a data quality issue. Data stewards are the data quality experts in charge of ensuring the quality of both the actual business data and the corresponding metadata. They assess data quality by performing extensive and regular data quality checks. These checks involve, amongst other evaluation steps, the application or calculation of data quality indicators and metrics for the most relevant data quality dimensions. Clearly, they are also in charge of taking initiative and to further act upon the results. The first type of action to be taken is the application of corrective measures. However, data stewards are not in charge of correcting data themselves, as this is typically the responsibility of the data owner. The second type of action to be taken upon the results of the data quality assessment involves a deeper investigation into the root causes of the data quality issues detected. Understanding these causes may allow designing preventive measures that aim at eradicating data quality problems. Preventive measures may include modifications to the operational information systems where the data originate from, such as making fields mandatory, providing drop-down lists of possible values, rationalizing the interface, etc. Also, values entered in the system may immediately be checked for validity against predefined integrity rules, and the user may be requested to correct the data if these rules are violated. For instance, a corporate tax portal may require employees to be identified based upon their social security number, which can be checked in real time by contacting the social security number database. The database administrator, DBA, is responsible for the implementation and monitoring of the database. Example activities include installing and upgrading the DBMS software, backup and recovery management, performance tuning and monitoring, memory management, replication management, security and authorization, etc. A DBA closely collaborates with network and system managers. He or she also interacts with database designers to reduce operational management costs and guarantee agreed upon service levels such as response times and throughput rates. Data scientist is a relatively new job profile within the context of data management. He or she analyzes data using state-of-the-art analytical techniques to provide new insights into, for example, customer behavior. A data scientist has a multidisciplinary profile combining ICT skills such as programming with quantitative modeling such as statistics, business understanding, communication, and creativity. In this chapter, we zoomed into the organizational aspects of data management. We clarified the critical role of metadata and the appropriate modeling thereof. We reviewed data quality and illustrated how data governance can contribute to it. The chapter concluded by reviewing key roles in data management: information architect, database designer, data owner, data steward, database administrator, and data scientist. The chapter is based upon our book, Principles of Database Management. In case you want more information, I'm happy to refer you to the website at the bottom.